Good morning. So this course is especially about the problems, the issues which we investigate in material science. And in the last few years, it is fair to say that materials selection depends also on the recyclability of the materials you have, and you select the materials also in terms of their availability. Here you can see a modified Mendeleev table which represents the amount of each element you have available at the moment. This might change, and you have also these phone icons, these smartphone icons, which represent which materials are used in smartphones, because it's an iconic object in the last few years, and it's an object that requires to use a number of materials, and it's an object as well which is difficult to be recycled, because before recycling anything, this is general, you are supposed to separate the different materials, which might not be obvious in the case of smartphones, for example. So what else? You can easily see that some materials are in critical situations, like it might be the case also for metals which you use quite a lot, like zinc, especially for coverage, also in alloys in some cases. And in other cases, you have materials which have got just one application, like indium, for example, which again are in a critical supply. So you need to recycle them. And we orient material selection to that. When I started studying material science a few decades ago, there wasn't that much concern about recycling, because recycling was at the beginning, because in most cases, when you use mainly steel can be molten, can be recycled with quite a good effectiveness. This is the case also for aluminium. It is quite effective to recycle aluminium. This is not a course about recycling, but we need to consider also this. And it is important to be aware of the fact that, for example, this is about smartphones, as I was saying before. Smartphones, there are some parts which are better known than others, and you use most of the elements in the Mendeleev table just to produce smartphones. In particular, you use rare earth metals for colors. We are going to discuss this little bit next time, where we are going to concentrate also on glass. And you use as a touch screen the indium tin oxide, which is a development of the metal silicon oxide chip, but it is transparent when compared to silicon oxide metal, semiconductor junctions and microchips. Then, of course, you have glass. Glass is mainly silica, might be also aluminum. You might have glasses also made with aluminum. And you have a battery, which is in most cases a lithium battery, which involves also the presence of cobalt. Then here we don't consider explicitly plastics, but there are plastics which are mainly made of carbon. Well, the main element involved is carbon, which we have plenty of, but as a material, plastics might be very polluting, and which we are going to discuss just a little bit when we are going to talk about polymers and plastics in the last part of the course. So this is the situation. Of course, you have to disassemble the phone. Disassembling means that you have to separate the different parts. Then you have magnets. You have magnets. We have already talked a bit about magnets, about the lanthanides used in magnets, like neodymium and praseodymium and so on. And of course, since these are magnets, we need to have one of the three main ferromagnetic elements, which are ferrite, cobalt, and nickel. In this case, we use nickel normally. Having said that, let's try to concentrate a little bit more on some parts of it. For example, indium tin oxide, it is used for smartphones screens, and they are conductive, which is not strange, and they are also um, transparent. It's a little bit strange instead that you have the two characteristics together, conductivity plus transparency. That's why ITO are so diffused. Indium is already in shortage of. We use it just for this kind of fields. The other uses of indium are really marginal. But despite this, it's already in shortage, so we need to work on it and to try to recycle 100% of it. The problem is, to be clear, is that you put together it with an oxide and with tin, which means that you have to separate the three of them. An oxide which in some cases you connect with glass, so you have indium and tin oxide, and you connect it with glass, and of course on the upper part of it you connect with metal, so to have a for example aluminum, because it's lighter and anyway it's conductive, and you have this kind of junction, which is a development of the normal silicon chip, which is a more recent one. Well, it came out in the 80s, so as for research applications. What are the developments? Well, this course is about research developments. Of course, in material science, as you may have realized, there are a large number of developments which are going on. So in some cases, it's not very easy to try to make sense of all these developments. But I ask you to concentrate on some developments which induce some curiosity, and whilst the written exam is going to be an open question on reasonably general topics, because you see that there are some topics that go around for the whole subject, for the whole of material science. For example, mechanical testing, for example, conductivity, for example, recyclability, etc., and crystal arrangement, and so on. Then I would like to have you writing this kind of educational paper on one topic of your interest, of your particular interest. Trying to concentrate a little bit on as far as the dimension of the topic is involved, because you might otherwise disperse, because the literature is really huge. So the developments are, as always, there is one theme which goes around a lot, which is about the including waste. In this case, they include cellulose nanofibril waste. So nanofibril taken off cellulose waste, which might be paper waste, or other types of cellulose which are not used exactly for papers. You can have cardboard and so on, packaging, etc. Here you have a kind of process, and what you find in the end is that you have this film with very precise, very precise and crystalline cellulose nanofibrils, which reduce the dimensional variations of the film you find, you produce in the end. And in practical terms, as always, the cellulose nanofibrils yield a precise ITO particle, precise ITO nanoparticle, because cellulose nanofibril results in a kind of scaffold, which has to be removed by the effect of temperature, by annealing. So you heat up quite quickly to get to a high temperature, and then the structure has been created, and therefore you get very precise indium tin oxide nanoparticles. We define a nano material, a material which has got at least one dimension which is lower than a micron. So it is in the order of the nanometers. As far as lithium is concerned, what we have basically, we have an anode which is made of graphite, which is not strange, and there is a charge and discharge cycle, which is interesting, that most batteries don't have the ability of move around electrons from one side to the other and to reverse also the cycle. Most batteries till the 80s, apart from lead batteries, which were rechargeable, developing on lead batteries, we were able to, the researchers were able to complete that cycle that allows not only discharge but also recharge. You have an anode into graphite with lithium, in combination with lithium, which allows you the conduction. Well, it's a metal. It is quite light. It has limited mechanical properties. Lithium, so in practical terms, it has never been used for structural application because of its low mechanical properties. But it produces crystals which instead have a substantial mechanical properties, but they are ceramic. And so the atoms move around from the structure to the other structure, and from the structure of one electron to the other one, and back, allowing that flux of atoms. And it is interesting, that structure, because that structure involves the creation of precise crystal structures. In particular, we have a rhomboedral lithium cobalt oxide structure, and which is created by that precursor, which is that cobalt hexa oxide structure, which is an octahedral one. In practice, you have a precise stacking sequence, which is the best one to allow electron circulation. And also, you have another factor, which is the temperature. The temperatures is very precise structure, as you can see the hexagons, which are shown in image A, which you don't find at other temperatures. As always, we try to heat the material as less as possible because it costs in terms of energy and so on. In this case, it works to stop at 600 degrees, as shown by this work by Rajan et al. But they have investigated quite a lot which was the right temperature to produce the right temperature for synthesis of these crystals. Of course, there is one consideration which is important to do. We have a charge and discharge. This is might seem trivial, but it is important to say that there is a charge and discharge, but this is not without any limit for thermodynamical reasons. Of course, you have some losses during these cycles, these charge and discharge cycles. So in the end, you get an end of life, and you have to dispose of this matter, which is another matter, which is might be another problem. And also to this, it's important to investigate. So we are always talking about material selection, and we are going to talk about also recycling. You might consider that recycling is always convenient. In reality, recycling is convenient depending on a few factors. First of all, there is an important statement which is necessary to make, which is that recycling means transforming geometrically the material. Then you have mechanical recycling. You grind the material and you reduce into powder or something like that. And then that powder is possibly, if possible, it's molten. It's brought to temperature and it melts. If the material has the right structure to melt, for example, wood doesn't melt, apart from the fact that there are some applications which allow wood melting in the last very recent years, but in normal terms, wood doesn't melt. It's built not to melt. So you stop there with wood. In other cases, you can have thermal recycling, so you have this kind of fluid, which then you can go further, and you can basically come back to the constituting elements. You can, for example, produce chemical recycling some types of plastics. You don't stop just at molten plastics, but you come back to the real chemicals. So, for example, from polyethylene, you can come back to ethylene and sell it as chemical. Apart from these general statements, I would have to say that there is a kind of recycling desirability. I found very suggestive this study, which is a recent one, which states something which is well known by many years, that the first statement is that we need to be able to separate the different materials. And for example, here we have to the right we have the main materials, for example, for batteries, the old lead batteries, which are still around, and it's becoming one of the major applications of lead, which has had a long history of use, also because lead is a metal which is very diffuse on Earth. But apart from that, it melts at quite low temperature, so it's quite easy to work. And in the case of these batteries for transportation, you have plastic, which is the case, which the batteries contain the electrodes and electrolyte, and then you have lead and electrolytes, which in the normal case was sulfuric acid. So which can be disposed of in a number of ways. For example, create in creating some sodium. You can separate some sodium sulfate crystals and so on, but there are a number of options anyway to dispose of this electrolyte. You can go into more details if you wish, but the question, the real question is that you need to be able to separate the material. This is a good case because in a sense, the battery for a car, it's a good case because you can easily, apart from some contamination, plastic that can be, for example, contaminated with lead because of the contact they have for possibly a long time. But apart from that, apart from some contamination, the materials are clearly separated: plastic, lead, and electrolytes in different ways. And which is good, you can put everything into a new battery, which is usually not the case into recycling. So this is a good case for recycling. In most cases, when recycling something, you are not able to reuse it in a new battery, in the same object, even in the same object. Then the material can be critical. For example, lead is critical. It can pollute water, which means that you need to be careful in managing it, and also you cannot manage it in a very simple way. You need to have a complex interaction with lead. So in this case, you have also a technology which is ready to dispose of everything. So you know that you know how to make car batteries since more than a century. So it's not easy to fabricate. It's not difficult to fabricate a new lead acid battery. In other cases, might not be the case. In some cases, you have not the technology which is ready to separate all the different materials to disassemble them, as it happens in most cases. For example, in smartphones, because they tend to be compact system, but with some parts which are welded, which are glued together, and therefore you are not very, you cannot very easily separate. Of course, there is also a consequence with cost, because I work on the technology if the cost is good enough to afford that. For example, wind turbine cost a lot. We don't know exactly how to disassemble wind turbines in many cases. In some cases, we may have some difficulty, but the cost is worth the price. And new methods are coming out more and more. You can see that at the other bottom, a PET bottle. It's easy because it's going soon to be just one plastic. Now it has still a polypropylene cap and ring. But apart from that, it will come in soon. Will be just one material, so it's already disassembled in a sense, and I can easily recycle it. But I cannot make a bottle with the recycled. I can put just a little bit of the recycled into a new bottle, into plastic for a new bottle, or I can make another object. For example, not transparent, of course, and with larger thickness and another type of object. So it's important in general terms to lose the fairy tale vision of recycling. Recycling might be difficult because I don't have the technology. I am not able to separate the materials, or I am managing difficult materials. I'm managing critical difficult materials, and the recycling process itself might be polluting for soil, for air, and for water. So ceramics tend to fail in different ways, tend to fail by cleavage fracture. Cleavage fracture is basically a shear fracture. So according to different planes, here you can see some examples, a silicate, some types of minerals. These are 4 types of cleavage in one direction, in 2 directions, or as it is mostly the case, in 3 directions, which might be in perpendicular directions, in 3 directions which are perpendicular between them, and in 3 directions which are oblique. Of course, this is a model. Be aware that the reality, which you see to the right, it's much more complicated. We have a material which is very well known, a ceramic material which is very well known, the lead zirconate titanate PZT. PZT, we are interested a lot because it constitutes piezoelectrics, which might work as actuators. We might use a piezoelectric for example, to lighten something, to lighten your oven, say. Or you can use piezoelectric as sensors. If you have an opposite piezoelectric effect, you may use them as sensors. In non-destructive testing, for example, or also in biomedical field, a lot of piezoelectric sensors are still used. They work well. They are not nanosensors, but they might be shaped in a way of making microsensors. The problem is that you have a case, of course, which includes the piezoelectric. Inside you have, and the case is not a problem itself. I can make a steel case. But inside I have a ceramic, which is the real PZT, the real piezoelectric. And I have to cut the ceramic to shape in order to allow it to work and to fix the case, which in some cases is not obvious. Remember that ceramic steel in most cases are produced by cutting them to shape. Then we will see other ways of producing ceramics next time. But in general terms, cutting is still an option and still a problem because you have not controllable cleavage fracture, and you can have flaking of ceramic and loss of material. Even in fabricating clay pots, you might have the fact that you lose 40%. In that case, you don't cut, you mold the vases, the pots, but you waste a lot of material because you have to interact with water and so on. So we are going to talk about cement a little bit, and this will give you some suggestions. The bone, it's a typical case of a ceramic, and you can see that bone has got it's a natural ceramic, of course, and bone has got a large number of ways of breaking. Bone is constituted from collagen. You have this triple helix of protein fibers, and you build these hydroxyapatite crystals, and then from this bone precursor you have the formation of the real bone. You pass up to micrometer dimensions, and you create that. Of course, this has in the end a number of different ways of breaking, which people working in medicine know quite well, like the green stick, which is typical of tooth in many cases. And then you can have a fissuration, which is not that strange fissuration, it's also into other materials, but in other cases, the comminuted and the spiral fracture in particular are not typical. For example, in metal, you don't find the spiral fracture unless you give a large torque to the metal. Otherwise, you wouldn't have a spiral fracture in tension inside that. Again, this is a model trying to summarize which kind of fracture you might have. Why do we care about how bone fractures? Because ceramic structures compare with our other materials, and they might be a model, there might be a model of the way we make materials. We try to investigate that because we want to understand how to stop the crack. That's a big problem in engineering, how to stop the crack. Because we don't have isotropic material, but we can try to make layered materials, and in making these layered materials, what happens is that we might have the fibers oriented in different ways. This is going to be called angle ply or cross ply. Cross ply when the fibers are disposed to 0, 90, or it is usually said no 90 degrees. Or we can have different layers at different, for example, plus minus 25, plus minus 45 degrees. We try to mimic, to reproduce a kind of quasi-isotropy. We are just trying, because the reality in ceramic, in natural ceramic, like in a number of structures like enamel, like shells, like ceramic shells from muscles, say. We have a reality of a number of layers with fiber. Each layer has got fibers in its own orientation, and they have also hierarchical structure. So in fact, they start from the cell and gradually they go up to the macro structure. The consequence is that they are much more isotropic, and the consequence is also that they are tough. They are able to stop the growth of the crack. Even if there is a loading direction, which might be in terms of compression, they are able also to withstand a little bit of tension, but even if there is a very strong compression, they are able to stop the growth of the crack in that direction, which is a problem which is very important, for example, for cement, concrete, and stone, and building materials, even in clay bricks. So we are thinking of, this is a diagram with written text, and we are trying to understand whether we can do a kind of composites which are able to reproduce natural ceramics, having a considerable Young's modulus and also a high fracture toughness, which is an ideal. Here they show that alumina and PMMA, which is polymethyl methacrylate, which you might know as plexiglass. Plexiglass on its own, it has reasonably low Young's modulus, so please be aware that this is logarithmic. Collagen, the original, you may see that from collagen to bone, collagen is the protein that forms bone. It's a mixture of amino acids that is the building brick of bone. For the hierarchical structure, you go up to bone, and you go up by 2 orders of magnitude in terms of fracture toughness, and almost so in terms of Young's modulus, just by hierarchization. That's why it's interesting. So you start from the nacre protein, it's even better. You start from the protein and you go up by 3 orders of magnitude, also in terms of toughness, and almost so in terms of Young's modulus. In practical terms, apart from using the real bones and the real nacres, which has also be done in history. Um, what we can see, we can imagine making composites, for example, with natural yet extracted composite like alumina and PMMA, polymethyl methacrylate, because it's a big problem. Polymethyl methacrylate would substitute, for example, glass. It costs less than glass, but as a matter of fact, it has lower toughness, and also it tends to deform with temperature. So we need a better stiffness. And making composites with alumina and PMMA is a possibility. So you have basically a ceramic alumina with a polymethyl methacrylate. Okay, and we are measuring the last few years. It's important to know because it's a sector which is important in material science. We can only give some details, just some details, but these are diatoms. Diatoms have got this kind of fuselage, which are basically they are monocellular diatoms. They are marine creatures, and they are made of silica. They have got this kind of silica cells, which, if you think of a glass bowl wouldn't have these characteristics of being so light and withstand deformation, to withstand deformation up to a considerable amount of strength, considering their very little dimension. We are talking about nanometers. And you can make nano indentation. Nano indentation is not very different from hardness because you always push with a tip and you create a kind of fracture. And after some, where you have applied some strength, and then you have a kind of well, you can see here you should recognize that we have an hysteresis. Basically, what they have done here, they have done. There is no really elastic behavior at this small dimension. There is always a kind of accommodation, a plastic behavior from the beginning, and in fact, is recognized by this kind of curve, which results in an hysteresis, so in sparing some energy. So basically, you have damage energy, which is recognized by this hysteresis curve. And so basically, you have this example of studies. There is always low displacement or stress strain. The question is that you say low displacement because you are not measuring really. It's going to be tricky to measure the section of the diatom. But anyway, you do low displacement, and you can make also some kind of cyclic curves. Because, of course, it depends also on, there is an effect of time, which you can see on to the right on the isochrone curves. There is an effect of time, and basically it depends on how much time you apply the load, and there is some variation into behavior, and not in going up, but in going down. That's basically you apply the load for some time, and then you find out that you have a slightly different behavior into recovery. The seconds would refer to the time that the load is maintained. You maintain the load for some time, and then you have a different way to recovery. So there is a kind of viscous behavior, and also there is a variation of viscous behavior. Has also another consequence, is that if the material was completely elastic, it wouldn't matter whether you pull it fast or slow. The, in other cases, if you have a little bit of viscous behavior, that means that you need to be aware of the fact that you have different behavior, whether you pull it fastly, say 100 millimeters per minute. That's what usually you do on tensile test. You set your tensile testing machine to a velocity of pulling. For example, you say 1 millimeter per minute, 10 millimeters per minute, 100 millimeters per minute. And it makes a difference. If the material was completely elastic, it wouldn't make any difference. In fact, for a ceramic, when you do bending tests, you usually don't do tensile tests on ceramic because they have a limited resistance to tensile force, and also because, as the consequence, they are not applied as bearer of tensile force. But you can pull a different. Usually, if you pull at different velocities, you get different results. Here, in this case, they have done also stopping at different loads. They have stopped at different loads, and they have reversed it to study the hysteresis cycle. So how much energy is really absorbed by a material. There is all a field of material science that studies damage, and you study damage, and of course you want to see how big is the hysteresis cycle. You want to widen, to broaden the dimension of the hysteresis cycle, because as you may know in cars, now if you have an accident, if by disgrace you have an accident, what the car is supposed to do is to absorb damage so that you are not affected. And which means that the hysteresis cycle needs to be as large as possible. So you would better use a polymer, a composite, which absorbs a lot of energy, resulting in large hysteresis cycles. So it's far from the ideal. If you use a pure steel, a ferritic steel, which is very close to the ideal, at least in terms of isotropy, you would not have in case of damage hysteresis cycle. As the consequence, the steel releases the energy and something else absorbs it, which might be our body, which is not good. Okay, so they have tried to do non-indentation. Is not just a characteristic of diatoms or measured materials. You can make non-indentation, for example, of a polycarbonate steel. Because these materials, polycarbonate is another polymer which came out after polymethyl methacrylate. It went into trend, into fashion in the 70s, and it is used to produce sheets. So it's a glassy polymer. There are rubbery polymers and glassy polymers. At the temperature they are used, which is usually room temperature. Polycarbonate, here you have a subsequent indentation at different depths with polycarbonate. There is a model they have done, and these are the real curves in nano indentation. So basically you have a nanotip which indents the material, and so you don't need to have a large thickness. You might have a thickness which is less than a millimeter. In case of diatoms, much less than a millimeter. So other considerations are important in terms of the fact that nature knows better. Well, you can see here some examples of how hierarchization is applied. You have layered structure called symmetry. You can have, these are the incisor teeth in mice, which have this kind of orientation, and you can see the kind of cross-fly structure. You have layers. The teeth are made in layers with different orientations. This is another diatom exoskeleton. The diatoms are interesting also in terms, in fact, in terms of interaction with water. They don't absorb water because their pores are so small, but they are able to interact with water. So to be able to be also to be kept into balance by the forces, the gravitational forces and the stream forces from water. So they have been studied as filters. Especially not making use of the real diatom, but to study the distribution of pores into diatoms, so to understand whether filter might be more efficient, because filters are not very effective, if you know, because otherwise, now we are seeing the problem with coronavirus masks. They are basically filters because they don't move, they don't do any killing, they don't fight against the virus. They are basically filters, but you don't want not the virus, because the virus is too small. The particles carrying the virus, like might be particles from sneezing, for example, water particles from sneezing carry the virus, and we don't want that these particles enter our and go in or out from the mask. You can see all the problems, all the discussion on the problems related to the construction of filter. As a concept, filter is a very, very simple object. In practical terms, it's an object. It is not very effective. That's why we study diatoms. And we study also this. For example, this is another example in C. The magnetite particles in this kind of bacteria, which are in water, which are kind of jelly substances, which for some complicated hierarchical structure, they are able to include these magnetite particles. So in practice, they are magnetic bacteria. Because there are a lot of studies about these topics, because the problem we have with magnets is that they are heavy. Magnets are usually heavy because we have, of course, ferrite, nickel, and cobalt. We have also lanthanides, which work a little bit worse than the previous three, but as a matter of fact, all of these are quite heavy. If we would have the jelly structure, which is magnetic, that would solve a lot of problems. Think of a magnetic glue. Magnetic glue would solve a lot of problems. Instead of making something magnetic, the very glue we put, it is magnetic already. That's why they study this kind of structure. Because we are able to produce glue which are sort of jelly, but they are not magnetic. We study ceramic materials, natural ceramic, also another aspect which is important, that we need to understand whether other materials, the so-called biocompatible materials, biocompatible means that it doesn't produce adverse reaction when implanted in the body. Bioactive, it's a step further, is that they do also something. For example, titanium might work well without the body, within the body, without producing reaction when stuck to a bone, when implanted together with a bone. And in some cases, it might also be bioactive, which means that it might contribute to healing. It's not just a mechanical support, but it also contributes, helps bone to reconstructing itself. We have three types, two types basically, and a third which is intermediate between the two. We have alpha titanium and beta titanium, and alpha titanium is stiffer, it's more rigid than beta one. So there are also mechanics consideration. There is also the question of which is the dimension. Titanium is very ductile, and we are able to work it also in nano dimension, which is good again because every natural material is a nanomaterial, so it's work with titanium as well. And we can have a kind of multifunctional, which means multifunctional means that it doesn't only heal the surface, but for example, it might also release some antibacterial substances, which is again interesting. There is a lot of research on the these healing biomaterials that assist healing. They are bioactive and they have also an antibacterial action. So they do something plus they fight against the bacteria. They do something in helping the bone healing, plus they have an antibacterial effect. Because when we started using some metals or some ceramic in repairing something in our body, their action was only mechanical. The bone doesn't stay together. We put something that mechanically helps the bone to stay together, but there wasn't a real interaction with bone. Also, there were lots of inflammation. We have solved this problem. There are materials that don't produce any inflammation, plus there are some materials which are able to aid in also in antibacterial action, in fighting the inflammation which is already present in this one. Not only they don't produce a new one, but they fight also the one which is already there. One of these alloys that work particularly well, biomaterials is a huge field. These are called biomaterials in general terms. Biocompatible materials are called biomaterials. They might not be bio. They might not be bio. Titanium is not bio at all, but it is a metal which is produced by industrial methods. But it is biocompatible, then it is a biomaterial. It is a huge field. There are a number of journals dealing just with biomaterials, just dedicated to biomaterials, but one of the alloys which works particularly well is titanium with 6% of aluminum and 4% of vanadium. Of course, when you talk about this kind of interactions, since bones tend to move their junction a lot, bones and junction a lot, it is important, it is suggested that the fatigue resistance is important. Why the fatigue resistance? Because when the bone, if you think that the titanium structure is stuck together in some ways, it's implanted with the bone, as the bone moves because of their junction, the bone in most cases doesn't move itself, but there are junctions that allow them to move, and anyway the forces are there, and so you need to consider the fatigue test. Fatigue testing, as always, in different directions depending on what you want to do. You might have a rotating and bending. You might have push and pull. So traction, tension, and compression. You might have torsion and bending, etc. Because you may remember, we have seen it before, the different ways of applying forces to a bone, which means in the end that they break in different ways and forces might be very complex. Therefore, this is trying to modeling what happens. So you have the so-called SN curves for titanium 6 Al, Al 4E. and we have this SN curve, and in practical terms, you can see that as far as the stresses go up, the cycles go up, the stress go down. So this is basically the stress amplitude at which the material breaks, depending on break by fatigue. It might break by monotonic testing, but this is not very interesting because if we implant the bone, we implant the bone for many cycles. If you implant on a femur, say, then our leg will move for 10, 20 years or so, and which means a large number of cycles. And of course, depending on the number of cycles, it will break at a lower rate. So it is inversely proportional with not a linear curve, with more than a linear trend. And also, please consider that, as always, this trend is a bit, I wouldn't say artificial. It is important. It is important to try to establish a trend, because in the end, what I am interested to is to guarantee what is the interest of person fabricating prosthesis in titanium prosthesis. The idea is that I can guarantee that it can undergo 1 million cycles, say, before it breaks. So I need to know the possible stresses which are applied on the femur, or on the tibia or whatever, and after that I need to be able to make some tests. The problem with this kind of test, or fatigue test, I will be clear about that. The problem with fatigue tests is that they are expensive, because let's imagine, well, you have 20, you might have 30 hertz, so rotating and bending for 30 times a second, or push and pull for 20,000 cycles a second, because in some cases we may assume, depending on where the prosthesis is, we might assume very fast moving. It is difficult to acquire data because these tests are a long time. So you use that fatigue machine for a long time. They tend to simulate these force applications, which is already a problem because they are not exactly push and pull or rotating and bending. They are something which looks like. Nonetheless, they are very important fatigue tests, give us indications, knowing which we need to be very cautious, and we possibly go lower than that. We try to guarantee for a lower number of cycles at a lower stress amplitude, and so we need to be cautious in guaranteeing, also from an ethical point of view, guaranteeing prosthesis. So you can see the type of problems we have here. So ceramics, what you might have realized is that ceramics break in strange ways, which are not the typical ways of metals, and which are quite repeatable. Well, you have a ductile, a brittle fracture. Here you can have complex ways of breaking, which are connected. In particular, they tend to be brittle, and they are connected with the dimension of the crack. This is of the flow, if you want, the defect. They depend on the flow geometry. They depend on the material, of course, so they depend on Young's modulus of the material. And there is a critical stress intensity factor, which it was important already for metals, for damaged metals, but it is much more important on ceramics, which is after you exceed in tension in this case, but in tension because it's easier anyway to measure when the crack starts to expand. But you can do that in other ways of loading, and and you get to a critical fracture energy, after which the crack proceeds with no hindrance, and you get to a fracture very suddenly. So these are the formula that relate them. So you have a critical flow size. You have a critical flow size which is correlated with the material, and it's correlated to, of course, the amount of the critical amount of stress and the critical energy after which everything propagates to fracture. A problem arises at this point that your flow is not circular. It could be supposed to be approximated to a kind of circular flow. Circular flow would simplify everything, but in reality, it's not circular, and it's not an academic consideration. If it is not circular, that means that the stress is not the same in all the points of the circumference, because there is no circumference. It's a quasi-circumference. If you see this is a broken sample, this is a half of a broken sample from which we try to make consideration under the microscope. And you can see that under the microscope we divide the fracture surface of the ceramic into three parts, which are mirror, mist, and aqueous. Basically, we try to take some measurements and try to model the dimension of the flow. To try to determine its correlation with fracture stress. Because the fracture in ceramics and in glass is sudden, which creates lots of problems. In particular, there is the Griffith theory, which is very important. Griffith was involved was a Navy engineer, and was involved in the disaster which happened with the Titanic ship in its first trip, which was 1912, and he started working on that in 1915. And because he realized one thing which was unknown at the time, that the ship was wrecked, was basically flooded because of the fact that the portholes exploded. And the portholes exploded because of the pressure of water, but because they had defects. Many of these had defects, which were not round defects, but they were sort of elliptical defects. The defect is usually elliptical because, and very pronounced ellipses. To start with, Griffith started to study a circular defect, and in a circular defect, he found out that the very fact that there is a defect in the sheet, the glass sheet, determined an increase of stress which was threefold, even if the defect was circular. In reality, the increase of stress is much more because the defect is elliptical, and this contributes to the fact that the stress really applied is not predictable. It's much larger than the real defect. The real stress we suppose to apply. And of course, when it exceeds a critical value, the crack propagation becomes unstable because we exceed the stress intensity factor, and in the end, a failure occurs. Griffith made a number of simplifying assumptions that there was no necking, there was an elastic propagation, and so on. In reality, glass is sort of elastic, but it might have some deformation, especially at the time, because then the technology of glass was improved so to reduce the real deformation, the real non-elastic deformation, especially the effect of the hot-cold cycles. In reality, the stress state produced by a crack under Griffith's assumption tends to be an ellipse, a very pronounced ellipse with very different, for example, alpha and beta angles with respect to the origin of the so we two semi-axes of the ellipses which have a very different dimensions. In reality, we can see that the formation of cracks might be quite complicated. This is a limestone which was subjected to a compression test, so in the end you might find on the surface a number of cracks which go in the most different direction because they tend also to coalesce. So it's still a very investigated problem of not easy solution. I think I will stop in here. We are talking now about glass. We will talk a little bit about glass, and it's going to be important then to move to other materials which have different, completely different characteristics, and when the plasticity would play a bigger role, and also the viscous effects and so on. So from glass, we are going to move then to concrete, where so the relation with water plays a role, and therefore to polymer and so we'll see you on Monday at 4 as always, and have a nice day and a nice weekend.
Thank you. Bye.
Bye.